This is my lab report for Lab 2, projectile motion. The purpose of this lab is to observe projectile motion in an experimental setting and to determine the forces acting on the projectile as it's in motion. I will also create a computational model that models the experiment both with and without the effects of drag. The fundamental principles of physics in this lab include constant forces, Newton's second law, or the momentum principle, and drag. In this experiment, the projectile being thrown is a paper ball in 2D, which is the system, while the Earth and its surroundings, while the Earth and surrounding air are the surroundings. The expected results of this experiment include both the x and y components of velocity, slowing down due to drag, and in the y component, gravity. The computational model with drag should yield similar results, but the model with no drag will maintain a constant x component of velocity, and the y component will only be affected by gravity. This is the tracker analysis of the experimental data from the video, which we'll play on the next slide. In this experiment, I threw a paper ball in the positive x direction in a parabola, emulating projectile motion. I used a meter stick to calibrate the video to get an appropriate distance. This is the computational model that accounts for drag. The trajectory is parabolic, while the drag opposes the ball's motion. The velocity in the x direction decreased due to drag, while the velocity in the y direction generally decreased, but not quite linearly due to the effects of vertical drag opposing gravity slightly. And this is the computational model that doesn't include drag. The key differences are that the ball travels further in the x direction, the x velocity doesn't change, and the y velocity is affected by constant in gravity. Also, the ball doesn't quite make it to the ground in the same time as it did when accounting for drag. This is the code for the computational model. With no drag, the b value is equal to 0, negating any effects of drag. I updated initial position and velocity to best match my experimental data. Then I applied the momentum principle to update the motion. To account for drag, I played around with the b value until I settled on b equals 0.19, which most closely models my experimental trajectory. And this is the graphical comparison of the trajectories of the experiment and the computational models. The tracker data represents the experimental data collected, and from this, it is obvious that the drag model more closely replicates the experimental findings. The model with no drag has a higher and longer trajectory due to less forces acting against its motion, hence why it overshoots the expected trajectory and doesn't land in the same time interval. There were many potential sources of error and assumptions made in this experiment. For example, the calibration of the displacement in the tracker may contain error, along with human error when recording and imperfect tracking of the projectile. In the computational model, I obviously assumed no drag for one of the models, but in the model with drag, the effects of drag are assumed to be perfectly distributed on the paper ball, which isn't the case experimentally. So in this experiment, terminal velocity was not modeled by any experimental or computational data because there simply wasn't enough free-falling motion in the time period to invoke terminal velocity. The closest model is the one with drag because that slowly negates gravity as the object is free-falling. However, for an object to reach terminal velocity, the drag force must offset gravity completely, giving a net force of 0, which simply wasn't true in this experiment. So what if instead of throwing the object in 2 dimensions, it was thrown straight up in 1 dimension? Would it come back down with faster or slower? It will take longer to come back down because the magnitude of speed is acting only in one direction now. So the vertical displacement will be greater, while the acceleration caused by gravity is still constant. This was also proven using the computational model. Ultimately, this experiment modeled projectile motion in 2 dimensions, both experimentally and computationally, and the effect of drag on the total net force was observed as a result. This net force then impacted the momentum of the ball, which ultimately impacted its trajectory. The findings from this experiment were that computational model with drag is closer to the experimental data than the model without drag, and the inconsistencies in this data, particularly between the experimental data and the drag model, likely come from the drag being unevenly distributed on the projectile. Thank you very much for watching this lab report.